nobody has ever come up with a convincing explanation for how photographic film worked on the moon, aside from the radiation and the heat and the cold and all the other problems which we actually do know about. Aside from the radiation and the heat and the cold and all the other problems which we actually do know about.
I meccanici della macchina a 100 gradi sotto si bloccano perché il metallo si restringe, il metallo si dilata, quindi le macchine fotografiche sono fatte a ingranaggi meccanici. Io non so mai.
Another problem connected with the cold environment is that at such low temperatures, the photographic film loses its flexibility, becomes rigid, and may easily break during the transport within the camera. Even though we are in the vacuum, the film touches the camera body all along its path. Since the camera irradiates and progressively loses heat, so does the film inside. And we know that below a certain temperature, photographic film becomes rigid and brittle, almost like glass.
Il problema è che la pellicola a meno 80 diventa cristallo, si rompe. Nel momento in cui carichi si spezza.
Quindi non puoi avanzarla?
Molto improbabile, cioè è stato sempre uno dei grossi problemi di lavorare all'estremo freddo, è che la pellicola diventa vetro. Freddo è micidiale.
A few months ago, it was a presentation being given in London by a gentleman who had worked on the spy satellites, the KH-9 hexagon spy satellite. He was very proud of his work. He worked on the camera equipment. One of the points he made, which I'd never heard made before, was he said, what we discovered was that when photographic film is exposed to a vacuum, it disintegrates. So because they were using photographic film in the spy satellites to photograph Russian rocket launches and all the rest of it. They weren't using digital back then. This is late 60s, early 70s, coincidental with Apollo. What he found, or what was necessary to be done, was that the photographic film had to be contained within a very slight pressurized environment. Only 1 pound per square inch was sufficient to maintain the integrity of photographic film, which is made from photographic emulsion. It basically starts life as a liquid. It's dried, but it still has the form of a liquid. The photographic film on the spy satellite had to go from the huge reels of film, containing about 30 miles of film, through the cameras, there were 2 of them, to produce stereo images, from there to the buckets, they were called, which were, get this, dropped from the satellite and captured by aircraft trailing vast fishing nets. Unbelievable to think of it now, but that's how they did it. And wow. That is for real. The point is that the photographic film in a vacuum of space, and we're talking well above the Earth's atmosphere, we're talking about 200 miles up, where the vacuum is quite strong, it would destroy photographic film, or it appears to have done, and that's why it was necessary. And we were shown very nice images of the tubes through which the photographic film had to be transported, and then the tubes were pressurized with nitrogen. We've shown the nitrogen gas canisters that we used to pressurize it, all the way through to being dropped out of the craft. Now, if that was required for photographic film in the late 1960s, what happened on the moon? We're still using photographic film, Kodak Ektachrome material, reversal film, slide material. Forget digital, we're not talking digital, we're talking photographic film.
Yes.
The moon has a far stronger vacuum than occurs in low Earth orbit.
We must ask ourselves whether the film containing the lunar pictures has ever been on the moon at all. For on this film, there is absolutely no trace of what should have been the damage caused by the radiation present in outer space. Cosmic space outside the Van Allen belts is filled with radiation of all kinds. You have solar eruptions hurtling through space alpha particles, protons and electrons at over 1,000 miles per second. And then you have ultraviolet rays, X-rays, gamma rays, and cosmic rays, which originate directly from the heart of our galaxy and are the most dangerous and penetrating of all. As explained in this documentary on cosmic rays, the fact that these particles are practically unstoppable is due to their extremely high velocity.
The key to cosmic rays' transformational energy is speed.
So even if it has really tiny mass, like most cosmic rays, they've got enormous velocity. So their kinetic energy can be really, really large.
These charged particles could hurtle right through a spaceship and penetrate astronauts like tiny ballistic missiles.
Obviously, if cosmic rays can penetrate spaceships, they can just as easily penetrate the body of a photo camera. And it's well known that all these radiations are very harmful to photographic film. This is explained by Douglas Arnold, who was assistant managing director for Kodak at the time of the Apollo missions.
You have an enormous amount of radiation in space, and potentially it affects film, of course, and of course, as you will well know, its prime effect is on contrast.
An extreme example comes from the pictures of Chernobyl. This is Igor Kostin, the Soviet photographer who shot some of the most famous images of the nuclear disaster of 1986.
I processed my pictures, and I noticed the negatives were black.
The effects of radioactivity are clearly visible on film. The emulsion shows some very heavy graining, and the colors are visibly altered. But even less powerful radiation can seriously damage photographic film. This technical bulletin published by Kodak shows the damage that can be caused to photographic film even by a single pass under an airport's X-ray scanner. On the left, an original shot. On the right, the same film after a single pass under the scanner. After 5 scans, the film is completely ruined, and the image is barely visible. This is a well-known problem to professional photographers.
Te prova a passare una pellicola ai raggi X di un aeroporto, pigli e butti via il lavoro. Infatti quando si andava a fare viaggi ci aveva la valigetta a parte oppure schermata col piombo.
Here's another example with a 400 ASA film. The difference after a single scan is quite evident. Contrast and color saturation disappear, and a general fog seems to be covering the entire image. Even with sensitivities closer to those used in the Apollo pictures, the damage caused by a single pass under the scanner is evident. The graining is present all across the picture, and it becomes particularly visible in the darker areas of the image. Here is another example at 200 ASA. A single pass under the scanner has completely ruined the blackness of the night sky. In the pictures from the Apollo missions, however, the skies are perfectly black. The color saturation is fully preserved, and there is no graining whatsoever in any part of the picture. And we must consider that the pictures from the Apollo missions have been exposed to cosmic rays, which are much more powerful and penetrating than simple X-rays. This educational film from the 1960s describes how cosmic rays leave a very evident mark on photographic film.
Well, we don't get a picture in the conventional sense, but the charged particles do leave identifying tracks behind. Here's an exposure which was made on a balloon flight. It shows a primary cosmic ray particle hitting a nucleus in the film emulsion. Also, you see an enlarged photograph of one of these emulsion plates.
We must keep in mind that this experiment was conducted with a balloon flight well below the Van Allen belts, where only a small part of the cosmic rays from outer space manages to penetrate. On the moon, however, you don't have the protection from the magnetosphere, and the amount of cosmic rays that can damage both humans and film is definitely much higher. This is explained by Dr. David Groves, an expert in photographic analysis.
We're protected on Earth by a nice thick atmosphere, and that combined with the magnetic field keep these ionizing particles away from us. On film, of course. In space, you're not offered that protection.
In fact, thanks to the probes that have explored the moon in recent years, we are able to quantify with some accuracy the fluxes of radioactive particles present in the cosmos. From this document published by NASA, we can read, "The cosmic ray flux per square centimeter of lunar surface per year contains an amount of particles that translates to 4.5 particles per second per square centimeter. This document, published by the National Council on Radiation Protection, offers a similar amount. 4 particles per square centimeter per second during a minimum of solar activity. This amount can be reduced up to 4 times during a solar activity peak. Thus, on the Moon, we have an average flux that can range from 1 to 4 radioactive particles per second per square centimeter. A true downpour of cosmic rays capable of penetrating any object they were to find in their path. Considering that the photo cameras have been on the lunar surface for up to 8 consecutive hours with no specific protection against radiation, each roll of film should have received tens of thousands of impacts from the cosmic rays, damaging the pictures in a visible way. Instead, the pictures taken by the astronauts show no damage whatsoever due to radiation. Colors are perfect, the contrast is fully preserved, and there is no visible sign of graining on the emulsion. This apparently inexplicable fact is remarked both by Douglas Arnold and David Groves.
If you look at the results, top quality duplicates, you can see that there appears to be no effect whatsoever.
I would expect to see on the transparencies evidence of small bright dots where a high-velocity nuclear particle had impinged on that film. I have no evidence whatsoever that this has occurred.
But how is this possible? After all, it's NASA itself in this document from the Skylab project who writes, "The radiation environment encountered during Earth orbital missions was studied extensively. The results indicated that the radiation environment could severely damage unprotected film. The energy level of the intergalactic cosmic rays, explains the document, is so high that no practical method exists for eliminating cosmic radiation damage. This degrading factor must be accepted, and, though significant, it should not be unacceptable for short-term exposure or with relatively insensitive film types." We then ask the following questions. Given that, according to NASA, no practical method exists for eliminating cosmic radiation damage, and that this degrading factor must be accepted, where is the degradation, significant but acceptable, that should appear on the lunar pictures? Given that this is the result of cosmic rays' impact on film within the magnetosphere, where radiation is weaker than in external space, can you explain why on the lunar pictures there are no visible signs of radiation damage? Given that this is the result of a simple X-ray scan, which lasts only a few seconds, can you explain why in the Apollo pictures, which have been exposed to cosmic radiation for up to 8 consecutive hours, there is no visible graining whatsoever? Given that the lunar surface gets hit by an average of 1 to 4 particles per square centimeter per second, and that the cameras have been out on the surface unprotected for up to 8 consecutive hours, can you explain why on the lunar pictures there are no signs of degradation due to the radiation?
Just to say that, if anybody knows different about photographic film being affected by extreme vacuum, I'd love to hear about it.